So the alkenes are different from the alkanes, but it's in a way. The way they're similar is they're hydrocarbons. Hydrocarbons mean they only contain hydrogen and carbon atoms. However, the way they differ is they are unsaturated. Unsaturated means that they contain a carbon-carbon double bond. So the simplest, because you've got to have a carbon-carbon double bond, the simplest you can have is ethene, and that is C2H4. So their general formula is CnH2n. That is for linear alkenes. You can obviously have cycloalkenes as well, where you have a double bond in a ring like so. So this would be cyclohexene there. So how does the double bond occur? This bond here, this is what you class as a normal single bond. We call that a sigma bond. So that results from just the overlap of the orbitals between the two carbon atoms. So each carbon has used 3 of its orbitals. So one's left over, and what's left over is a p orbital, like so. There's an electron in that orbital and an electron over there. So what they do is these two guys overlap above and below the carbon-carbon single bond, this sigma bond, to give you this double bond here. Can anybody, do you know what that bond, if that's a sigma bond, this is a, oh no, it's actually a pi bond. So that's a pi bond. So it's the overlap of a p orbitals above and below the sigma bond. So this is an area of high electron density. So that's going to attract, have you come across the term electrophiles before? Okay, well it will attract things called electrophiles. Phile means love, electro, so it's a reagent which loves electrons. Yeah, so hydrophilic means it, yeah, okay. Philic is that. So that is your pi bond. Now, if you take your models, you can't rotate around that pi bond. If I take this, if that's my pi bond, and I try and rotate, what's going to happen? What have you got to do to that? You've got to break it. So that takes a lot of energy. So you can't do that. So what I'd like you to do now is I'd like you to make but2e. So now you've made, so this is but2e. Before we get into the nitty gritty of isomerism, let's just think about bond angles. So look at your models. What's your bond angle around this carbon here? What's that bond angle? Around, you've got a double bond. No, that'd be tetrahedral. This is 120 degrees. And why is it 120 degrees? How many centres of negative? We class this as being 1. So I've got 1, 2, 3. So 3 centres of negative, well, bonds, because we class this as 1. So that means you've got, it's a trigonal planar bond. Okay. What about around these bonds here? Around each of those carbons, what are your bond angles? So that is your tetrahedral centre. So this is tetrahedral. So what they do is they mix up the questions and ask you to talk about bond angles in organic chemistry. So you always just think how you do it. So this double bond class is 1 bond. So there's 2 types of isomerism that these guys can do. The first one you should be okay with. So if I've got butene, I can have 2 types of butene. I've made you make but2e, like so, where you've got CH3, CH, then your double bond, CH, CH3. What other one could you have? But1ene, brilliant. But1ene, which would be CH2 with your double bond on the end, like so. So that is structural isomerism, where I've got the double bond in a different place. Stereoisomerism is something that may be new. So these are stereoisomers. So on this one, hopefully you can see, if that's my double bond there, I've got my 2 hydrogens pointing up and my 2 methyl groups going down, and I can't turn that around. If I look at this one has got the 2 hydrogens on opposite sides and my 2 methyl groups on opposite sides. So this is stereoisomerism. The bonds and the atoms are in the same order, but these, the hydrogens, are across from each other, and here they're on the same side of each other. And this results because I've got different groups on the carbon atoms, and I cannot rotate around a double bond. You try rotating around, the only way you can do that is if you break that bond. Please don't break it. Okay, so those are 2 types of stereo isomers of butene. Could you have that type of stereoisomerism for but1ene? Well, I'm going to say no. And why is that? Well, let's draw it out. For but1ene, it's going to be CH, like so, then your double bond, then CH, and then going down CH2, CH3. If you change that, what would it be at the moment? You've got the H's on the same side there, but you swap it, you've still got the same, haven't you? You've got to have different groups here for you to have different types of isomerism. So there's 2 types. There's where if you draw it, you've got your H's on the same side, and I think you would have talked about this in the basic concepts, and on this you've got them on the opposite sides, like so. So there's 2 different ways you can do it. This would be called the cis isomer, and this is a trans isomer, but you've also talked about EZ isomerism. Okay, so you haven't talked about EZ isomerism. So these, are we happy at the moment that these are 2 different isomers of each other? So we've just got to work on how we name them. So if you just pop the models down for a minute. So we've just got to work on how we name these, and we'll do some examples. The way we look at it is we look at the priority. So we look at them in terms of the atomic number of the atom connected. So what's the atomic number of hydrogen? 1, well done. What about carbon? 12. Okay, and then again we've got 1, 1, 12, 12.
Carbon's atomic number 6.
Oh, no, you're right, yeah, it's 6.
Oh.
Yeah. 6, 6, 6. Okay. Oh, too many 6s. That's not good. So, what we look is, we look at how the highest priority groups are arranged. So out of all of these, carbon is a higher priority group because that's got a higher atomic number. Are my highest priority groups on the same side or different side? They're on the same side. If they're on the same side, that would be called the Z isomer. So that would be called Z but2ene. For this one, my highest priority groups are on opposite sides. They've got to see across that double bond. So this would be called E but2ene, like so.